a shrinking shoreline, towering white mineral rings climbing canyon walls, empty boat ramps stretching farther into the desert each passing year. Those images have become the defining symbols of Lake Mead's crisis, convincing millions that the reservoir has only one problem and only one possible solution: more water. But is that assumption hiding a much larger story? Can a reservoir facing decades of declining inflow also be losing something just as valuable beneath its surface? If engineers cannot manufacture more water for the Colorado River, is it possible to recover the space that was originally built to store it? Those questions are beginning to reshape conversations about one of the most important reservoirs in the United States. Rather than searching only for new sources of water, a growing engineering discussion is examining whether restoring lost storage capacity could become another tool for extending the life of Lake Mead. It is an idea that sounds almost impossible at first, yet it is grounded in a challenge that every reservoir on Earth eventually faces. For generations, nearly every discussion surrounding Lake Mead has focused on drought, declining snowpack, shrinking river flows, and growing demand across the American Southwest. News reports frequently highlight the reservoir's falling water level, the famous white bathtub ring visible along the canyon walls, and the difficult decisions facing the states that rely on the Colorado River. Those concerns are real and continue to shape water policy across the region. Yet hidden beneath the lake's surface is another process that has been unfolding quietly since Hoover Dam was completed during the 1930s. Every year, the Colorado River carries enormous quantities of sand, gravel, silt, and clay downstream from mountains, canyons, and tributaries spread across several states. Before the construction of Hoover Dam, much of that sediment continued its long journey toward the Colorado River Delta. Once the dam blocked the river, however, the current slowed dramatically as it entered the expanding reservoir, allowing those sediments to settle onto the lake bottom instead of continuing downstream. That gradual buildup may sound insignificant when viewed over the course of a single year, but reservoirs are designed to operate for generations, not seasons. Over nearly 9 decades, thin layers of sediment have continued accumulating across different parts of Lake Mead. Grain by grain, flood by flood, the reservoir has slowly been surrendering part of the space that engineers originally intended to hold water. This process is known as reservoir sedimentation, and it represents one of the most predictable consequences of building large dams anywhere in the world. Unlike evaporation, which changes from year to year depending on weather conditions, sediment accumulation creates a more permanent reduction in storage capacity unless the material is physically removed or somehow transported downstream. While Lake Mead still retains most of its original capacity, scientists and engineers have long monitored these deposits because understanding how the reservoir changes beneath the surface is just as important as measuring the elevation of the water above it. The reason sediment settles so efficiently inside reservoirs comes down to one of the most basic principles of physics. Rivers possess energy, and that energy allows them to carry particles ranging from microscopic clay to coarse gravel. Fast-moving water flowing through steep canyons can transport remarkable amounts of material over great distances. But when that rushing river suddenly enters a vast reservoir, everything changes. The current slows, turbulence decreases, and gravity begins taking control. Larger particles settle first, followed by sand, then finer silts, and eventually the smallest clay particles. Over many decades, these deposits gradually reshape the underwater landscape, creating layers that can be measured through bathymetric surveys, sonar mapping, and sediment core samples. These technologies allow scientists to compare the reservoir floor over time, revealing changes that remain completely invisible to people looking across the calm surface from the shoreline. Understanding these hidden changes also requires understanding an important engineering concept that rarely appears in public discussions about Lake Mead. Not every gallon of water stored inside a reservoir can actually be used. Engineers divide reservoir storage into several categories, including active storage and dead storage. Active storage refers to the water that can normally be released through Hoover Dam to supply cities, farms, industries, and hydroelectric generators downstream. Dead storage, by contrast, lies below the lowest outlet structures and cannot flow through the dam under normal operating conditions. Sediment tends to accumulate in the deepest portions of reservoirs because gravity naturally carries material downhill across the underwater landscape. As those deposits slowly build upward, they gradually occupy space that once held water. Every cubic foot filled with sediment represents another cubic foot that can no longer store future inflows, making sedimentation an issue that directly affects the long-term performance of reservoirs across the globe. That realization has inspired a fascinating engineering thought experiment that differs dramatically from the usual conversations surrounding Lake Mead. Instead of asking only where additional water might come from, some engineers and researchers have explored another possibility. What if part of the lost storage space could be recovered? Rather than allowing sediment to remain permanently trapped beneath the reservoir, could massive excavation equipment remove enough accumulated material to restore some of the original capacity? It is important to emphasize that this is not an approved government project, nor is it an officially adopted solution. Instead, it represents an engineering proposal that examines whether existing dredging technologies could theoretically be expanded to a scale rarely attempted anywhere in the world. The idea immediately captures attention because it shifts the focus away from creating more water and toward preserving more room for the water that nature already provides during productive years. Dredging itself is far from a new technology. Around the world, ports, shipping channels, navigation canals, and harbors rely on dredging to remain operational. Without periodic removal of accumulated sediment, some of the world's busiest ports would gradually become too shallow for large cargo vessels. Rivers are dredged to improve navigation, reservoirs are occasionally dredged near intake structures, and flood control channels often require maintenance after major storms. Engineers have developed several specialized systems capable of moving enormous amounts of material beneath the water's surface. Among the most powerful are cutter suction dredges, floating machines equipped with rotating cutting heads that loosen compacted sediment before powerful pumps transport the material through pipelines as a water and sediment mixture. Hydraulic dredging systems operate continuously for long periods, making them particularly effective when projects involve exceptionally large volumes of fine sediments. Scaling those technologies to Lake Mead, however, would create one of the largest excavation challenges ever considered for a reservoir. Lake Mead stretches for approximately 112 miles, or about 180 kilometers, when near full capacity, winding through countless coves and steep canyon walls. Any attempt to recover a meaningful amount of lost storage would require moving extraordinary quantities of sediment over many years, perhaps even decades, depending on the project's size. Massive pipelines could carry sediment slurry toward processing facilities, while mechanical equipment might separate water from solid material before transporting it elsewhere. Engineers would also need detailed geological surveys to determine the exact composition of the deposits, because coarse sand behaves very differently from fine clay during excavation and transportation. Every stage would demand careful planning, extensive environmental review, and enormous financial investment before the first significant amount of sediment could even be removed. Perhaps the biggest question raised by this concept is surprisingly simple. After removing millions of cubic yards of sediment, where would it all go? Disposing of such immense quantities beside the reservoir would create its own environmental and logistical problems. For that reason, engineers often explore what they call beneficial reuse, a strategy that treats dredged material not as waste, but as a valuable resource. Depending on its composition, sediment could potentially support highway construction, large infrastructure projects, mine reclamation, habitat restoration, or the rebuilding of eroded landscapes. Some coarse materials might even serve as construction aggregate after proper processing, while finer sediments could find uses in carefully managed environmental restoration efforts. Before any of that became possible, however, every deposit would require detailed chemical testing to ensure that the material met environmental and engineering standards. What initially appears to be nothing more than mud on the bottom of a reservoir could, under the right conditions, become part of entirely different projects across the region, adding another layer of complexity to an already ambitious engineering proposal. Even if engineers successfully overcame those logistical challenges, another question would immediately follow. Would removing accumulated sediment actually solve Lake Mead's biggest problem? The answer depends entirely on what someone expects the project to accomplish. Supporters argue that restoring storage capacity could provide meaningful operational benefits for decades to come. Every cubic foot reclaimed from sediment becomes available once again to hold water during years with abundant snowpack in the Rocky Mountains. Greater storage flexibility could allow reservoir managers to capture more runoff during exceptionally wet seasons, helping prepare for future droughts. Deeper navigation channels could also improve recreational access for marinas and boat launches that have repeatedly struggled with declining water levels. In some localized areas, carefully managed sediment removal could even improve water circulation or reduce the buildup of fine material near important intake structures. These are practical engineering advantages that focus on extending the useful life of one of the nation's most valuable reservoirs rather than replacing it. Yet, supporters of megadredging are also quick to acknowledge a reality that no excavation project can overcome. Removing sediment does not create a single additional drop of water. It restores space, not supply. If the Colorado River continues delivering less water because of prolonged drought, higher temperatures, and changing snowpack patterns, a larger reservoir will still remain partially empty. This distinction is perhaps the most important point in the entire discussion. Lake Mead's long-term challenge is not simply that it has lost some storage capacity beneath the surface. The larger concern is that the river feeding the reservoir now produces significantly less water than many planners expected when Hoover Dam was designed during the early 20th century. Climate scientists have documented declining river flows across much of the Colorado River Basin, driven by warmer temperatures, increased evaporation, earlier snowmelt, and drier soils that absorb more moisture before runoff ever reaches rivers and streams. Even if every cubic yard of accumulated sediment disappeared tomorrow, those broader climatic forces would continue shaping the reservoir's future. The financial implications make the proposal even more difficult to evaluate. No reservoir on the scale of Lake Mead has undergone continuous dredging at the level required to recover a substantial portion of its storage capacity, making precise cost estimates extremely challenging. Such a project would likely require fleets of specialized dredges operating for many years, extensive pipeline networks, processing facilities, transportation infrastructure, environmental monitoring, and a workforce capable of sustaining one of the largest civil engineering operations ever attempted in the American Southwest. The total investment could reach many billions of dollars before completion. That enormous price tag naturally raises another debate among engineers, economists, and water managers. Would those billions produce greater long-term benefits if they were invested elsewhere? Some experts believe the same funding could permanently reduce water demand through agricultural modernization, urban conservation programs, leak reduction, advanced irrigation technologies, wastewater recycling, and groundwater recharge projects. Others argue that preserving existing infrastructure deserves equal attention because reservoirs remain essential even if future supplies become less predictable. Environmental considerations also demand careful examination before any large-scale dredging project could ever move forward. Although Lake Mead is an artificial reservoir, it has evolved into a complex ecosystem supporting fish populations, migratory birds, recreational opportunities, and sensitive shoreline habitats. Large dredging operations inevitably disturb bottom sediments, temporarily increasing suspended particles within the water column. That change can reduce water clarity, affect aquatic organisms, and potentially release nutrients trapped within accumulated deposits. Construction activity would introduce additional vessel traffic, noise, shoreline infrastructure, and temporary habitat disruption across portions of the reservoir. Federal and state environmental reviews would almost certainly require years of scientific analysis before approving a project of such unprecedented scale. Engineers would need to demonstrate not only that dredging could restore storage capacity, but also that environmental impacts could be minimized through careful planning, monitoring, and adaptive management. Public participation would become equally important because communities throughout Nevada, Arizona, California, tribal nations, environmental organizations, recreational users, and agricultural interests all depend upon Lake Mead in different ways. Another challenge often overlooked is that sediment never stops arriving. Every spring runoff, every thunderstorm, every flood, and every erosion event throughout the Colorado River Basin continues transporting new material downstream. Even after an enormous dredging campaign, fresh sediment would gradually begin accumulating again. That reality has encouraged engineers to examine complementary strategies designed to reduce sediment before it ever reaches the reservoir. One promising concept involves sediment bypass tunnels, engineered systems that divert sediment-rich floodwaters around reservoirs during high-flow events so that much of the material continues downstream instead of settling behind dams. Other proposals include upstream sediment traps that intercept material before it enters major reservoirs, along with watershed restoration projects that reduce erosion through healthier forests, stabilized stream banks, improved land management, and wildfire recovery efforts. While none of these approaches completely eliminate sedimentation, they could slow the process enough to preserve reservoir capacity for much longer periods. Increasingly, engineers recognize that protecting reservoirs begins far upstream, across thousands of square miles or thousands of square kilometers, where the health of the watershed ultimately determines both water supply and sediment delivery. That broader perspective explains why the future of Lake Mead cannot depend upon a single engineering project, no matter how ambitious it may be. The reservoir represents only one component of the much larger Colorado River system, which supplies water to millions of people across 7 United States and parts of Mexico. Every decision involving Lake Mead affects agriculture, municipal water systems, hydroelectric generation, recreation, tribal water rights, environmental restoration, and interstate agreements that have evolved over many decades. As the basin adjusts to a warmer and more variable climate, water managers are increasingly relying on advanced forecasting models, satellite observations, improved snowpack monitoring, high-resolution bathymetric surveys, and sophisticated computer simulations to guide operational decisions. Technology continues providing better information than ever before, yet it cannot eliminate the difficult choices surrounding water allocation. Every gallon conserved, every improvement in efficiency, and every enhancement to existing infrastructure contributes to a larger strategy focused on resilience rather than dependence on any single solution. Ultimately, the debate surrounding mega-dredging succeeds because it challenges one of the most common assumptions about Lake Mead. The reservoir's future is not determined solely by how much water flows into it each year. It is also shaped by the physical space available to store that water and by the gradual geological processes quietly altering the reservoir beneath its surface. Restoring some of that lost capacity could extend operational flexibility, improve certain aspects of reservoir management, and buy valuable time during future wet years. Yet buying time is fundamentally different from solving the Colorado River's structural water deficit. Lasting security will almost certainly depend upon a combination of aggressive conservation, smarter water management, expanded wastewater recycling, healthier watersheds, continued scientific monitoring, interstate cooperation, and carefully selected engineering projects where they provide measurable benefits. Mega-dredging may one day become part of that conversation, but it is unlikely to stand alone as the answer. The real plan to help safeguard Lake Mead is not finding a way to manufacture more water. It is recognizing that every available tool must work together to protect both the water the Colorado River can still provide and the precious storage capacity that generations of engineers worked so hard to create.